Welcome everyone to this edition of Energy Briefs. Today we are here with Dr. David Tew and Dr. Bob Ledoux to talk about machine learning and the machine learning portfolio within ARPA-E and some of the next steps in terms of new programs that we might want to think about. So with that, I'll start with Dave with the first question. Dave, one of the key things that we want to talk about here is the Differentiate portfolio. Can you talk a little bit about that program and some of the key accomplishments Differentiate as it relates to machine learning?
Sure. Well, thanks, Rakesh. Well, Differentiate is focused on the development of machine learning enhanced design tools with the goal of enabling energy engineers to be more productive in the development of technology-based solutions to our energy and climate problems. In essence, we're seeking to develop energy technologies faster. And we're doing so by focusing efforts on the development of two tools that are intended to accelerate the pace at which engineers iterate to develop solutions to a specified problem. These tools ideally will include domain expert optimizers or hypothesis generators to develop new ideas faster, as well as accelerated hypothesis evaluation tools that enable engineers to evaluate those new concepts that much faster. And lastly, for targeted applications, we're actually trying to develop the ability to avoid iteration completely and generate near optimal designs instantaneously in a single pass from requirements via the development of what are called generative or inverse models. Now, within the Differentiate program specifically, we've been working for the past couple of years, as you mentioned. We've developed, I would say, all three capabilities successfully for a range of energy applications. We have domain-specific optimization capabilities for electrical circuits, battery materials and molecules, as well as chemical synthesis processes. Also, we've developed a range of ML-enhanced evaluation tools, or what are called surrogate models, which are being developed to enable the instantaneous assessment of performance of candidate designs for a range of different applications once these models have been trained. And lastly, we have generative models that are capable of providing instantaneous near optimal designs of turbine blades, for example, as well as photonic devices.
Thanks, Dave, for that. And so, Bob, we'll move on with a question for you. So, you've been involved with machine learning specifically around our nuclear fission and fusion portfolio. Can you talk a little bit about the efforts there and also talk about how some of the Differentiate projects could relate to some of those projects?
Well, thanks, Dave, for that great overview of Differentiate. There's a number of fission and fusion programs that overlap very directly with Differentiate, and I'm sure Differentiate will make a difference to them. I think the two most important ones are new materials development. And in our fission program, that's particularly relevant to making, for example, new waste forms or different processes in which the underlying difficulty in both producing new materials and then testing them puts a real premium on attempting to really shorten and accelerate the development process. And so Dave mentioned that in chemical processes, combining physics-constrained models, then do the testing, and then go through the machine learning to accelerate that development is very important. Another thing that's very important about that Differentiate is teaching all of us is really the connection between difficult physical models. For example, on both fusion and fission, radiation damage in new materials is very important, and we don't have a good physical model for that. So the hope on a couple of the projects I'm involved in is that maybe that the combination of literature search, quantum chemistry calculations, testing, and radiation damage measurements, that parts that are difficult to get a fundamental model for, that whole machine learning design phase that's very heavily weighted in Differentiate will really make a difference. So that's one. I think the second most important one is in the Gemini program, in which we are attempting to make digital twins for a nuclear power plant, mostly to reduce the operation and maintenance costs. There, of course, you would love to have sort of a high fidelity physical model for every aspect of the nuclear power plant, but that's just not possible. So is there a way of really sort of reducing the computational burden by using lower dimensionality physics models combined with operational data eventually, such that you can do a much better job with a much lower computational burden? And I think also in the design phase, it would be advantageous to do the same. So I think those are the two most important overlaps I think would differentiate. And I'll just throw one more that's very important. It's in a couple of the nuclear projects, which is really just trying to correlate data that is very orthogonal, both in processes and safeguards, such that you have a nuclear measurement, a radiation measurement, combined with a process measurement. And can we, do machine learning such that we can do a much better job at pulling out any deviations from the acceptable practice? So yes, I think differentiate can make a tremendous difference in nuclear.
All right, so with the final question, obviously we want to talk about what some of the key challenges are in terms of broader implementation of these tools so that they can actually accelerate product and process development across industries. Dave, you want to take that in terms of some of the key challenges that you see?
Sure. I think within the Differentiate program, we've clearly demonstrated that these methods do work for the targeted applications. I think the question becomes, do they always work well enough to justify their training cost, which is substantial? And the answer is probably no. But I think really what we need is a better way to kind of assess what the cost of training these algorithms might be before we start. Because in some sense, there's a decision folks have to make. Do I want to invest in training these ML algorithms in the hope that it'll make my design optimization process cheaper, or do I want to go via traditional methods? And that is a question to which we don't necessarily have crisp answers today. In some problems, the answer will be go the ML route. In other problems, the answer will be use traditional approaches. But at the same time, the cost of training is really the cost that you're going to pay to use these types of tools. We'd like to find ways to reduce the cost of training in future problems. And there are a couple techniques that are available. One is the concept of transfer learning, where you transfer knowledge from one problem to another problem, but basically by using a neural network you might have trained for one problem and move it to a similar problem and use that old neural network as the initial condition for your training process. And that may reduce the amount of training data that you need to yield an algorithm with a given fidelity. At the same time, trying to carefully select what data points you need to yield an algorithm of a target fidelity is something that is very, very important. So what it comes down to, we need to understand the cost of developing these algorithms better, as well as trying to understand how do we reduce that cost via some of these techniques that have been out there for a while, but we'd like to carry them that much further.
Bob, same question, key challenges?
If you look at the trajectory of machine learning historically, AI in general, once you get kind of a spectacular success where you show like machine vision did or whatever, once you show a real success that this makes a difference, then I think you get the most important quantity applied to it, the proper manpower with the proper training. So I hope through Differentiate, we get some great examples that convince stakeholders that this does make a difference. Maybe not in every case, as Dave said, but in many cases, it makes a big difference. And once you have those cases, then I think that basically, people in this domain will flock to use those new tools. And then I think you need the next step, which again happened in machine learning then you just need standardized tools that you don't have to relearn them every time you use them. And so we know that in machine learning and so on, the scikit-learn, TensorFlow, just a whole tool set that you can pick up and you can try applying it to every problem. Sometimes maybe apply it to the wrong problem, but you need that whole ecosystem of examples, trained manpower, and I think a really robust toolkit that you can apply to problems such as Differentiate tries to make a contribution to.
Yeah, and to conclude, I think from a key challenge perspective, on the commercialization side, it's all about pricing and value proposition. As the simulation tools are established, it's all about conveying to the customer how these simulation tools will help them build better products in a faster way so that they can go to market faster and hopefully they're cost neutral or even cost competitive, some of the existing simulation tools in the market. So with that, I'd conclude and thank you both, Dave and Bob, for your useful insights here on today's Energy Brief, and we'll see you next time.